Hey everyone, and welcome. Today, we're going to go on a bit of a quest for speed, for elegance, and for brilliance, all inside the world of code. We are diving deep into one of the most important ideas in all of programming, algorithmic efficiency.
I mean, you've been there, right? You open up an app and it just chugs along. Maybe it drains your battery. Well, another one just flies. What's the deal? Well, the secret isn't some kind of magic. It's usually buried deep in the code, in the cleverness of its design, and how smart the algorithms are.
So, here's the game plan for today. First up, we'll talk about why speed is so ridiculously important in the first place. Then, we'll tackle two big challenges, finding something called the greatest common divisor, and then we're hunting for prime numbers. And through those, we'll see how to make our code way better. And finally, we'll wrap up with some tools to make our code not just fast, but also really strong and reliable.
All right, let's kick things off with the big why. Why should we even care about this stuff? Well, the simple answer is that the world we live in is massive. We're not dealing with a handful of numbers anymore. We're talking about just insane amounts of data. And how we handle that data, that changes everything.
I mean, just try to wrap your head around this. Imagine you had to write a program to sort every single Adar number in India. A slow, inefficient approach might literally take days to run, but a smart, efficient one, it could get it done in minutes. Same thing goes for searching a huge company database or powering a real-time game where every single millisecond is the difference between winning and losing. Slow code isn't just a minor annoyance. It can make things completely impossible.
So, the real secret to all this speed? It comes down to one thing, minimizing operations. Think of it like a recipe. You could have a really bad recipe that says, add 1 single grain of salt, stir. Now add another grain of salt, stir, and you do that 1,000 times. Or you could have a recipe that just says, add a teaspoon of salt and stir once. Both get you a salty dish, right? But one is obviously way faster. Our job as programmers is to write the smartest, most efficient recipe for the computer to follow. Okay, you ready? Time for our first big challenge. We're going to find the greatest common divisor, or GCD, of two numbers. This is a classic problem, and it's the perfect way to show that journey from a slow, kind of obvious solution to something that is just truly brilliant.
First things first, what even is the GCD? It's just the biggest number that divides into two other numbers perfectly. So for example, take 8 and 12. The numbers that go into 8 are 1, 2, 4, and 8. For 12, it's 1, 2, 3, 4, 6, and 12. So what's the biggest number on both of those lists? It's 4. Simple enough, right? The real question is, how do we teach a computer to figure that out?
Okay, so here's our first shot of this, and honestly, it's the way most of us would probably think to do it first. We make an empty list, then we loop through all the numbers, and if a number divides both of our inputs, m and n, we stick it on the end of the list. When the loop is done, we just grab the very last number we added, and yeah, it works, but creating that list and storing all those numbers takes up memory, and it's just kind of clumsy and slow. Now, this next version is a little bit better, a definite improvement. We just get rid of the list entirely. Instead, we just keep track of the most recent common factor we've found in a single variable. This is great for saving memory, for sure. But the real problem is still there. We're still checking every single number one by one. If our inputs are huge, this is still going to take forever.
And this is where things get really cool. This is the big leap. On the left, there's a method that uses subtraction. But look at the problem. Finding the GCD of 1 and 1,000 would take almost 1,000 steps. But on the right, we have something called Euclid's algorithm. And instead of subtracting, it uses the modulo operator, that little percent sign. It just gets the remainder of a division. And this is a total game changer. Its speed isn't based on how big the numbers are, but on how many digits are in the numbers. That difference is absolutely astronomical.
So, how does this ancient piece of magic actually work? It's based on a surprisingly simple but totally genius idea. The GCD of two numbers is the same as the GCD of the smaller number and the remainder. So we just keep repeating that process. Each step makes the numbers we're working with way smaller, until bam, we hit the answer. It's an incredibly elegant solution that's been around for thousands of years. All right, quest number 2. We're moving on to the prime number hunt. Just like finding the GCD, figuring out if a number is prime is a huge deal in computer science, and it gives us another amazing lesson in how to think smarter, not harder.
So, quick recap, just so we're all on the same page. A prime number is any number bigger than 1 that only has two factors, itself and the number 1. Like 2, 3, 5, 7, 11. These are the fundamental building blocks of all numbers.
So the obvious way to check if a number's prime, right, is to find all of its factors, and then just check if that list of factors is just 1n. But think about how incredibly wasteful this is. To check if some gigantic number is prime, you're making the computer do all of the work of finding every single one of its factors first. We can do so much better.
But here is the brilliant shortcut. It turns out if a number n has a factor that's bigger than its square root, then it has to have a matching factor that's smaller than its square root. What does that mean? It means we only have to check for factors up to the square root of n. Look at the while loop in the code. For a huge number like 1 million, instead of doing 1,000,000 checks, we only have to do about 1,000. That is a gigantic, massive improvement.
Okay, so we've got speed down. Our code is lightning fast. But what happens when something goes wrong? What if a user types in something weird? A fast algorithm that breaks easily isn't very useful. So for our last section, let's look at a couple of tools that help us build code that's not just fast, but also robust and well-organized.
You know, when you're coding, there are all these little landmines waiting for you. Your code might accidentally try to divide by 0, or maybe it tries to grab an item from a list that doesn't exist. Any one of these errors can make your whole program just crash, which, let's be honest, is a terrible experience for anyone using it.
So how do we build a safety net for our code? We use something called exception handling. Look at this structure. We put any code that might be a little risky inside a try block. Now, if an error happens, the program doesn't just die. Instead, it jumps down to an except block. And in there, we can handle the problem gracefully. Maybe we show the user a friendly message. This is how you build software that doesn't fall apart.
And for our last tool, we're going to talk about a super powerful way to keep your code clean and organized: classes and objects. The easiest way to think about it is this. A class is like a blueprint for something, say, a car. The object is the actual physical car you build using that blueprint. It lets us bundle up data and the functions that work on that data all into one neat package.
Check this out. Here's a blueprint, a class called point. It's designed to represent a single dot on a graph with an x and a y value. That init function sets it all up. But here is the super cool part. Look at that add function. We are literally defining what the plus sign should do when we use it on our point objects. We're teaching Python a new trick.
And here's where it all pays off. We create 2 point objects, P and Q, from our blueprint. And then we can just write print P plus Q. It's that simple. Because we defined that custom add behavior, Python knows exactly what we mean. Add the x's, add the y's, and give us back a new point. The result is a new point at 812. It's just a much cleaner, more intuitive way to write complex code.
So at the end of the day, that gap between a clunky app and a beautiful fast one, it all comes down to the cleverness of the code, that journey from a brute force guess to a truly brilliant solution. So the next time an app on your phone feels a little slow, just stop and think, what's going on behind the scenes? What elegant algorithm is just waiting to be discovered to make it fly? Thanks for coming on this quest with me today.